So the work that I do really deals with some of the things that are going on here in Alberta, the oil and gas industry. And we know we can get some unique properties when we use nano-sized materials. But how do we somehow get our nanostructure or nano-sized material into something useful or anything which is sizable? So there are a number of ways we can do this, but why develop them in the first place? Well, we know that they have some unique properties and we can make use of those properties. So in the general oil and sands industry here, what we find is that you've got this industry that's suffering, industry that suffers from all kinds of problems, and we could use materials that can reduce the amount of degradation through both abrasive, erosive, and corrosive type of wear. So the potential of these coatings is given here, and basically we can expect significant increases in hardness. We can also expect to see some corrosion resistance. One of the things that we want to get away from is that the industry currently uses simple heat-treated materials. In other words, taking thick sheets or plate material that has been heat-treated and it's welded into place to prevent degradation. So by using much thinner coatings which have wear resistance equivalent to, or if not better than what we're doing at the moment, we can substantially increase efficiency in that way. The other thing is that we can also treat all kinds of shapes and sizes as well. So contours is an important thing as well. So at the university, we're looking at two separate regions. One is the use of WC, tungsten carbide based materials, and also we're looking at some more novel coatings where we want to be able to treat inside pipelines as well. We've got listed here different compositions. In fact, there's a wider number of families of compositions that we're looking at, but there are patenting issues and we need to deal with those before I can talk about them. But certainly there are novel types of coatings that we're using where we're using these special kind of coated powders, duplex coated materials. How are we doing this? How are we transmitting what we have in powder feedstock to surfaces? Well, when we're trying to deal with nanomaterials, we're trying to prevent processes that cause the nanostructure to lose its nanostructure. And many of these processes involve some kind of heating. So that is a bit of a challenge from a materials engineering point of view. So after a lot of extensive comparisons of different types of coating methods that we can use, we came down to using this particular process, and it's known as the high velocity oxyfuel spraying process. There's lots of different types of spraying processes, but for retaining nanostructure, this is one of the processes that is the most effective. So we're producing a jet, there's an explosion that takes place in a chamber, and we shoot out the powder. Now there are two ways in which we can develop nanostructure. We can either develop it during the spraying process itself, or we can start off with a feedstock powder which has a nanostructure. So we've taken the easy route. We've taken the nanostructured powder and we feed it in through the gun over here. We feed it in, and the explosion and the fuel mixture allows us to deposit onto the substrate surface. So this just to give you an idea of the kind of surface morphologies and the sizes that we're dealing with. This is a microstructured powder, and this is a nanostructured powder which has a cobalt layer on the outer surface as well. What we see is that the powder finish is much finer with the nanostructure, and that has some unique effects on the processing, the spraying process itself. What we find is that the feedstock powder can be sprayed more efficiently. There's less coagulation or starvation when we're trying to spray some of this powder, and the overall spraying efficiency is increased as well. When we've sprayed the material and it's sitting on the surface, when we cut through this coating and we look at the microstructure, this is what we see. The microstructure here, the microstructured powder, and this is the nanostructured powder. There's some distinct differences there. What we tend to call homogeneity or homogeneous types of coatings. What we find with the microstructure is that you can here see the tungsten carbide, WC powder distributed randomly throughout the coating itself, but here you can't see the carbide dispersion whatsoever. And one of the reasons is that we've got a much finer dispersion that's spread throughout the coating. And that does different things to the chemistry of the powder as well. We're also using a matrix, which is cobalt, but we're also protecting the powder with using a cobalt layer outside as well. That does different things to the powder. It helps flow, but it also helps cement or bind the WC dispersion within the coating. So we want to look at the mechanical properties, and we can do that simply from a number of tests. So normally when we're talking about wear resistance, we try to correlate that with coating hardness. And if we compare the untreated sort of steels that are used in this industry, it's a carbon manganese steel, we get sort of hardnesses down here. This is untreated. This is the treated hardened steel. It's been tempered as well, so it has some toughness. This is the microstructured coating, and then we have the nanostructured coating up here. So there is this difference in hardness. We've managed to maintain some of those properties that we want from the nanostructured powder. If we look at the abrasive wear resistance, the ASTM G65 is one of the industry standard tests. This is the heat-treated material and the microstructured coating, and then the nanostructured coating itself. So there's a substantial difference between what we have currently that tends to be used in industry, and then the microstructured and the nanostructured material. If we just compare the nano and the microstructured powders, then we tend to find something like a 6-fold increase in the abrasive wear resistance of the powder. Yeah. Great, thank you, thank you. Okay. So what are we doing? What are we trying to do here? Well, basically this schematic tries to explain that with the microstructured material, we're packing much more here, but with a nanostructured material, we can pack much more dispersion strengthened material. And what it does is it reduces the distance between the particles as well. And the effect that has is that it improves fracture toughness of the coatings as well. What we tend to find is as hardness increases, normally materials become more brittle. That lowers the fracture toughness. But here, with the nano-sized materials, the nanostructured material, we tend to improve fracture toughness as well. So this is a measure of some of that fracture toughness. It's looking at the wear mechanisms. And so when we compare the surface, we find that this is the nanostructured material. It's a finer surface finish. When we quantify this using atomic force microscopy, the red line indicates the surface roughness taken from the nanostructured surface, and the white lines here indicates the microstructured coating. When we examine surfaces closer to see what are the mechanisms, we find that these pit markings are much larger for microstructured and much finer for our nanostructured. So basically, there's a change in the wear process itself. Because we're maintaining the fracture toughness of the coating, then we can expect a change in the wear mechanism. And so here we see the nanostructured materials, there's these micro groovings, and that shows the material is still ductile and plastic. This is brittle fracture, and this is seen in the microstructured coating. This is a direct comparison of the changes in fracture toughness. So here we have our microstructured coating. This is a nanostructured coating. I've kept it very simple. There's much more data that I could have presented. I was told this is a talk for a couple of minutes, so I'm pushing myself. So this is just an erosion corrosion test. We usually can't ignore the corrosion aspect that takes place in this industry. So we were tempted to put this data here as well. And the nanostructure material shows us much better erosive corrosive behavior as well. So these are just some general applications in the pump industry, different types of pumps and materials that tend to show this kind of erosive wear, and these can be treated. And I've also listed a whole load of areas where there is potential applications for these coatings. I can't ignore this without my researchers. They're the ones who produce this data. This is why I'm standing here and presenting this work. Okay, thank you.